Bismillahirrahmanirrahim. Hello students, welcome to the Electrical Engineering channel. This lecture will be based on the discussion of a dipole and the value and or expression of potential and electric field due to a dipole will be derived in this lecture. So dipole can be defined as the combination of equal and opposite charges, two equal and opposite charges separated by a distance d. This is called a dipole. So dipole is basically two equal and opposite charges separated by a distance d constitute a dipole. And here we are given a dipole in which a positive q charge is located over here and negative q charge is located over here. So the dipole axis is actually the z axis, and the separation between these two charges is d, and the orientation of this dipole is along the z axis because both of these charges are at the z-axis, and at this point P, which is located far away from this dipole compared to the distance between these two charges, and at this point we have to evaluate the expression for potential and electric field. So the distance of this point from this positive charge is r1, the distance of this point from this negative charge is r2, and this dipole is located at the origin. So the center of this dipole is at the origin, and the distance of this point from origin is r, and this is equal to theta, which is the definition of theta and r in spherical coordinate systems. So v will be equal to q over 4 pi epsilon r1 minus q over 4 pi epsilon r2 due to these two charges and at this point p. So if this point P is far away from this dipole such that the position vector R is much greater than this D, right? So if this R is much greater than this D, then these three position vectors R1, R1, R and R2 can be assumed as parallel position vectors. So this is R1, this is R and this is R2, and we can draw a line from this point up to this point such that the angle between this line and this R2 is 90 degrees. So under this condition, uh, this vector from this point up to this point will be equal to R2 minus R1, right? So beyond this line, all these three vectors have equal length. So R1 will be equal to R2, but beyond this point. So it means the difference between R2 and R1 is equal to the length of this vector. So this vector is actually R2 minus R1. So if this is 90 degrees, this angle is 90 degrees, and we know that this angle is theta and this angle is also equal to theta, then this D vector can be um divided into two components. This is the horizontal component and this will be the vertical component. So this horizontal component of D will be equal to D cos theta, and this vertical component will be equal to D sin theta. So R2 minus R1 will be equal to this component and it is equal to D cos theta. That is the thing which is written over here. So this V can be simplified as Q over 4 by epsilon. R1, R2 can be taken as LCM. So we will have R2 minus R1 over here, and R2 minus R1 is equal to D cos theta. And R1, R2 is approximately equal to R square, right? Because R1 is less than R and R is less than R2. So the product of R1 and R2 will be approximately equal to R square. So this is the expression for V. And using this expression, we can evaluate the electric field intensity. And from the previous lecture, we know that electric field intensity is equal to minus gradient of V, and in spherical components, E will be equal to this expression, right? So this uh, potential has actually only two components in it, right? It has the R component in it and it has theta component in it. So this phi component is not present in this expression. So this will be equal to 0. And we can evaluate the partial derivative of V with respect to R and partial derivative of V with respect to theta. So by taking these two derivatives, the expression for E will be equal to QD over 4 pi epsilon r cube into 2 cos theta AR plus sine theta A theta. So we can evaluate the equation of the streamline, right? In spherical components, the equation of streamline will be E theta over ER equal to R d theta over the dr. And E theta is equal to QD over 4 pi epsilon R cube into sine theta. And ER is equal to QD over 4 pi epsilon R cube into 2 cos theta. So when we divide these two components, E theta over ER, then we will just have sine theta divided by 2 cos theta. So this sine theta over 2 cos theta will be equal to R d theta over dr. And here, from here, we will get a differential equation, right? So this is the differential equation which we can solve easily. So dr over r will be equal to 2 cos theta over sine theta d theta, and this will be dr over r integral is equal to 2 cos theta over sine theta d theta, and this is equal to natural log of r equal to 2 natural log of sine theta plus natural log of c, and this can be simplified as natural log of sine square theta. This 2 can become the power of this argument of the natural log, so it will be ln sine square theta, and these two natural log terms can be multiplied together, so it will become ln c sine square theta. By taking the anti-log, it will become r is equal to c sine square theta. So this is the equation of the streamline, and we can plot this equation for different values of c, and we will see such circles, right? So for a value of c equal to 1, we will get such a ring. If we increase the value of c, the radius of this ring will go on increasing, and similarly for negative values of c, we will get such rings over here. And these are the streamlines, right? And I will define another term which is called a dipole moment, and dipole moment can be defined as the product of magnitude of charge and the distance between the two charges in a dipole, and that is called a dipole moment. Dipole moment is also a vector quantity because q is scalar and d displacement is actually vector, so p is also a vector quantity. So dipole moment is product of q and d, and for potential we have this expression V is equal to QD cos theta over 4 pi epsilon r square. So QD is equal to P, which is a dipole moment, Q multiplied by D. So it will become P cos theta over 4 pi epsilon r square. And P cos theta can be written as P dot AR. So V will be equal to P dot AR divided by 4 pi epsilon r square. And if the dipole is not present at the origin, then it will become 1 over 4 pi epsilon r minus r dash magnitude square into p dot ar, and ar is equal to r minus r dash vector divided by r minus r dash magnitude. So this is the expression of potential due to a dipole at point P, and this is the expression for electric field due to a dipole at point P. And from this expression r is equal to c sine square theta, we have plotted the streamlines, and using this expression V is equal to QD cos theta over 4 pi epsilon r square, we can plot equipotential surfaces, right? So these are equipotential surfaces. So this is the first surface, and at this surface, the value of potential is equal to 1, and the value of potential is actually proportional to the value of cos theta, right? So V is equal to QD cos theta. So when we have theta equal to 0 or 180 degree, we will have non-zero values of potential, and for a value of theta equal to 90 degree, potential will be equal to 0. So that is the thing which we observe in this figure. So here theta is equal to 90 degrees, and here potential will be equal to 0. So we don't see any equipotential surface over here. But at this axis, theta is equal to 0 degrees. So equipotential surface as the maximum potential, and here the theta is equal to 180 degrees, and potential will be negative for these equipotential surfaces. And here r is equal to 1, sorry, here V is equal to 1 because R is small. So as we go on increasing R1, the value of potential is decreasing, right? Because potential is inversely proportional to the square of the distance. So when we increase R, the potential will decrease. So here again, this thing is observed. So when we go on increasing R, the value of potential is decreasing in the negative direction over here because theta is 180 degrees and here theta is 0 degrees. So it is go on increasing in the positive direction. So let's solve an example to illustrate more the concept of potential due to a dipole, and here we are given a dipole moment of 6 Az nanocoulomb meter at origin, and let's calculate the potential uh, due to this dipole, right? So V is equal to P cos theta over 4 pi epsilon r minus r dash magnitude square, and at the for the given point r is equal to 4, at which we want to calculate the potential. So all the quantities are known, and potential will be equal to 54 by 16 cos theta, and this is the point at which potential is to be measured. So this is equal to 54 over 16 cos 20 and 3.17. Similarly, E can also be evaluated, and E is equal to P over 4 pi epsilon r cube, right? Because here we had QD and here we have 2 cos theta AR plus sin theta A theta. So all the quantities are known and we can substitute all the quantities R and theta in this expression, and the final value of electric field is 1.586 AR plus 0.288 A theta volts per meter. So that is all about our discussion on dipole. Hopefully you have understood all the concepts in this lecture. For watching more videos, please subscribe this channel. Until the next lecture, it's goodbye.